I'm going to be discussing backtraces in this presentation. I will discuss why backtraces are important, implementation of backtraces in Ruby, why production of partial backtraces was slow in older versions of Ruby, and how we fixed it in Ruby 3. I'll also discuss bugs that occurred as the result of the optimization and how we fixed those bugs. My name is Jeremy Evans, and I'm a Ruby committer who mostly works on fixing bugs in Ruby. I'm also the author of Polished Ruby Programming, which was published a few months ago. So this book is aimed at intermediate Ruby programmers and focuses on teaching principles of Ruby programming, as well as trade-offs to consider when making implementation decisions. Oh, sorry, my bad. All right, so backtraces. Why do we care about backtraces? Well, I mean, consider programming without backtraces. I mean, let's say you're working on a refactoring in your library, and after working on it, you run the tests, and it turns out that one of the tests fails with an argument error with output similar to this. So this output tells you you have an error and what type of error it is. But without a backtrace, you have no idea where the error is occurring, which makes debugging much more difficult. Okay, so backtraces themselves are important. But how important is backtrace performance? I mean, specifically partial backtrace performance. I don't actually know the answer to that question. As I mentioned, I focus most of my time on Ruby on going through the bug tracker and fixing bugs, not implementing performance improvements. However, it happened that another Ruby committer filed issue 17031 on the issue tracker regarding partial backtraces not being optimized. And the other committer mentioned that they found this issue when checking memory usage in RubyConf. In any case, this performance issue was filed as a bug, and since I fix a lot of Ruby bugs, I did some research into it. Now, this was the first time I had looked at how backtraces were generated in Ruby, so it was a learning experience for me. I think how Ruby generates a backtrace is interesting. I'm guessing most of you are unfamiliar with the process, as I was before working on this optimization, so I will go over this process now. So before understanding the backtrace generation process, we need to understand what backtraces actually are. So as in most programming languages, backtraces in Ruby are a representation of the call stack. So let's start off with an example of a call stack. We start with a method foo that calls bar with a block that calls caller. And we explicitly pass 0 as the argument to caller. So this makes the backtrace include the call to this method. And the default value for caller's first argument is 1, which excludes the call to caller. So then we have the bar method just yield. To see the results of the backtrace, we'll use puts foo. And these are the results. Note that the dashes here represent the file name. In this case, I was providing the Ruby code to execute on the standard input, in which case Ruby uses a dash to represent the file name. Now the first entry in the backtrace is the call to caller inside the block that you pass to pass to bar. Each call to a block is a separate entry in the backtrace. The second entry in the backtrace is the yield inside bar, which is the same as calling the block that was passed to bar. And the next entry in the backtrace is the call to bar inside foo, and the last entry in the backtrace is the call to foo in the main script. So I mentioned earlier that the backtrace is a representation of the call stack. If you read the backtrace from the bottom to the top, you can see how each call was added to the stack. In the main script, you call foo, which called bar, which called the block in foo. So let's dive into how backtraces are generated. I mentioned that backtraces represent the call stack, but Ruby does not have a call stack as a separate data structure. Ruby uses a virtual machine to execute code. In order to execute your Ruby code, Ruby compiles your Ruby source code into bytecode that is executed on the virtual machine. The virtual machine then processes the bytecode to do the execution. Now, the virtual machine keeps track of the execution of the current method or block using a virtual machine control frame, often abbreviated to VM frame, control frame, or just frame. The virtual machine tracks these control frames using a stack. Each time a method or block is called, the VM pushes a frame onto the stack. When the method or block returns, the virtual machine pops the frame from the stack. So I just described something that sounds a lot like a call stack. But earlier I said Ruby does not have a call stack as a separate data structure, which appears to be a contradiction. So the reason for this difference is that the virtual machine control frame stack, it's not exactly a call stack. There are control frames that are not considered part of the call stack and are ignored during backtrace generation. So we'll see later that these ignored frames that are not part of the call stack ended up causing bugs in the optimization of partial backtraces. So like most parts of Ruby, the implementation of backtraces is written in C. So backtrace handling is implemented in Ruby's vm backtrace.c file. So to make the backtrace generation process more understandable to Ruby programmers, this presentation is going to translate the algorithm used into Ruby pseudocode. I will also simplify it slightly to avoid parts that are not important to this discussion. So we'll start with a description of the backtrace generation process used in Ruby 2.7, which is mostly the same for older versions of Ruby, to describe the process before this optimization. So the backtrace generation process starts with the virtual machine's end control frame. And while it says end control frame, this is the starting frame for backtrace generation. Since the Ruby 2.7 backtrace generation process starts at the earliest control frame and then runs towards the current control frame in the order that each frame was added to the stack. Now, the first two control frames after the end control frame are dummy frames from the perspective of backtrace generation. So we'll ignore those. Let's assume that control frame's next method returns the control frame pushed after the receiver. Now, since the backtrace is returned as an array, we'll initialize an empty array for it, and the backtrace generation process will iterate over the remaining control frames. It needs to know the total number of frames and have a counter that is incremented for each control frame to ensure that it does not process off the end of the control frame stack. So the majority of the backtrace generation process happens while iterating over the control frames, which we'll do here using a while loop. At the end of each loop iteration, we will move to the next frame and we'll increment the counter. So here's the main part of the backtrace generation algorithm, and let's go over each step. As I mentioned earlier, there are different types of virtual machine control frames, and not all of them are considered during backtrace generation. There are only two control frame types considered during backtrace generation. These are ISEQ frames and cfunct frames. ISEQ stands for instruction sequence, and ISEQ frames are usually, but not always, frames for normal methods defined in Ruby. Cfunct stands for C function, and cfunct frames are frames for calling methods defined in C. So ISEQ frames and cfunct frames have to be treated differently during backtrace generation because methods defined in C do not have file or line numbers associated with them. So the location of cfunct frames is determined to be the same as the preceding ISEQ frame. And this is the reason that the backtrace generation process starts at the earliest control frame and runs towards the current control frame. So backtrace generation does not use all of these ISEQ frames. It only uses ISEQ frames that have an instruction pointer or a program counter. ISEQ frames without an instruction pointer can occur for internal functions that call blocks, such as enumerables group by method. These frames should be ignored, as otherwise a single method call would result in multiple backtrace entries, and one of them wouldn't have location information because the location information is determined using the instruction pointer. So for the ISEQ frames that have an instruction pointer, these represent methods defined in Ruby. So in that case, we need to use the location information for the current ISEQ frame for any future cfunct frames until the next ISEQ frame. So we record the location of the call of the current control frame so that we can use it later when creating the backtrace entry for a future cfunct frame. So after recording the location, we add the backtrace entry to the array, storing the backtrace. Now for cfunct frames, we also add the backtrace entry to the array storing the backtrace. However, creating the backtrace entry for a cfunct frame requires knowledge of the last ISEQ location, so we pass that in when creating the entry. So after this entire process completes, we reverse the backtrace array because we want the backtrace ordered from the most recent call towards the oldest call. And finally, at the very end of this process, we use the arguments provided to caller to extract the entries of the backtrace that we're interested in. Now, caller's default start value is 1 and the default length is 0, meaning all backtrace entries after the first entry. Now, hopefully this shows why partial backtraces are slow. They basically require doing a whole bunch of unnecessary work. For example, if you want the most recent caller entry before the current method, you would call caller with 1 as the start entry and 1 as the length. And this would return an array of at most 1 backtrace entry. However, to get that array of at most 1 entry, Ruby will still create backtrace entries for most or all of the control frames before filtering it to only the frames requested. So the problem was fairly clear. Ruby is doing unnecessary work that will be thrown away. And the solution was also fairly clear. Now we needed to stop doing that unnecessary work and only add the backtrace frames that we care about. So as a first start of implementing the solution, we need to consider the start and length arguments passed to caller. Now in this initial example, we'll assume that the start and length were both provided, and that the start added to the length is still less than the number of control frames. So let's walk through the changes in this example. So instead of iterating over the total number of control frames, we'll use the start argument passed to caller to reduce the number of iterations, which we'll store in a variable named last. We'll subtract the desired length of the backtrace from the number of iterations to determine the starting point where we want to actually start adding backtrace entries to the array. We'll still iterate from the same control frame that we did in the previous implementation. However, until we reach the starting point, we only record the last ISEC location for every ISEC control frame with an instruction pointer. We don't actually add backtrace entries. We need to do this so if the last entry in the return backtrace is a cfunct frame, it will have the correct location, even though the location that it comes from is in an ISEC frame, which is not in the return backtrace. So I mentioned in this initial example, we will assume that the start and length were both provided, and that the start added with length is still less than the number of control frames. But the caller can provide arguments where the length is nil, or the start plus the length is greater than the number of control frames, in which case this logic is not sufficient. We're going to replace it with this to handle the cases. And if the start argument passed to caller is greater than the number of frames, caller actually returns nil instead of an empty array. If the start plus the length is greater than the number of frames, or no length argument is provided, the starting point for backtrace generation needs to be set to 0 so that the backtrace generation process starts at the outermost frame, the main script. So this is basically the algorithm that Ruby 3.0.0 shipped with. It passed all tests and specs and resulted in much faster partial backtraces in situations where the remaining control frames, I think about 6 times faster from about 400 frames. So I was quite pleased with myself. I was declaring victory over this long-standing performance issue. Unfortunately, this optimized algorithm is suddenly wrong. It took a whole month after the release of Ruby 3.0 before someone reported problems with it. However, it was reported in issue 17.581, this optimized algorithm could result in missing backtrace entries. So the way the algorithm is implemented, it's implicitly expected that the loop iteration will result in a backtrace entry in order to arrive at the expected number of entries. The problem occurs when you have an ISEC control frame without an instruction pointer. In that case, an iteration occurs without adding a backtrace entry. So if you're past the start iteration, where there is you come across such an ISEC frame without an instruction pointer, it will result in that many missing backtrace entries. So the solution here is to decrement the counter if this happens, and this ensures that you generate the desired number of backtrace entries. However, then in certain circumstances, you can process off the end of the control frame stack. So to make sure you do not do that, you need a separate counter that is compared against the number of control frames, and this ensures that even if you were skipping control frames, you don't process off the end of the control frame stack. Again, I was quite pleased with myself. I declared victory again over this issue. I was able to fix the regression quickly and easily. And unfortunately, well, that change fixed the case where the backtrace was missing frames. After the fix was committed, it was found to have broken a test case in Rails. Sorry. This was not broken after the original optimization. Now, unfortunately, neither the Rails developers nor I were able to construct a self-contained example showing this problem, which complicated debugging. However, Rails developers were able to provide a way to reproduce this issue using the Rails test framework, which enabled me to debug the issue. And later, after the fix for this issue was developed, before it was committed, another Ruby committer was able to construct a self-contained example showing this problem, which they posted as a note on the bug tracker. And this example was included as a test case when the fix was committed. So it turns out the cause of this issue is very similar to the cause of the previous issue. It occurred when dealing with ISEC control frames without an instruction pointer. So instead of missing a backtrace entry, as in the previous issue, it would result in an incorrect backtrace entry. For example, it could result in caller without an argument being treated as caller with a start argument of 0. So there were 2 changes needed to fix this bug, one simple and one complex. And the simple fix is that we need to ensure that we do not process frames after the requested start frame. So this is the issue that can make caller without an argument act like caller with a 0 start argument. We make this change by subtracting the caller start argument from the number of backtrace frames. So we basically adjust the initial size of the backtrace. This is to ensure that we don't process control frames that the caller has asked us to ignore. We then adjust the related code that uses the caller start argument to assume that the call or start argument is 0, since it has already been used to adjust the size. And here's the whole complex fix. And the purpose of this fix is to adjust the starting frame for backtrace collection so that we are trying to ensure that the optimized process will result in the correct number of frames. As this text is quite small, I'm going to zoom in for the explanation. So we only need this fix if we have a backtrace that's limited in both directions, where the start argument to caller is not 0, and it's given a length that is shorter than the actual number of frames. We scan the entire backtrace from the outermost frame towards the most recent control frame, again, looking for ignored frames. Check for ignored frames is the same as before, ISEC frames without an instruction pointer. If you come across an ignored frame that's before the starting frame in the backtrace, we need to flag that because that case will require additional work later. Otherwise, we just decrement this I counter. Now, at the end, the difference between these I and J counters is the number of ignored frames. Now, if there are no ignored frames, we don't have to do anything. Otherwise, additional work is required. If there aren't any ignored frames before when we expect to start backtrace generation, then we can just subtract the number of ignored frames from the start. Otherwise, the process is significantly more involved. We first need to scan to the expected start control frame. Then we need to scan backwards from that control frame, decrementing the start and the number of ignored frames until there are no ignored frames left. If during this backward scan we come across an ignored frame, we have to increment the number of ignored frames. And this did fix this issue. And we'll fix this ship in Ruby 3.0.1. And once again, I could claim victory over this issue. However, personally, the feeling of victory is quite hollow in this case. When you look at the code required for the optimization, it's complex. It does not bring joy. The workarounds required to make the existing backtrace algorithm work with the optimization is far more code than the algorithm itself. This optimized approach gives us performance, but at what cost? So as I was developing this presentation a few months ago, I came to the conclusion what we needed was not an optimization of the previous algorithm, but an entirely new algorithm. Instead of working inward from the end control frame, we need to work outward from the most recent control frame. Theoretically, this should result in a significant performance improvement in partial backtraces because we only scan the control frames that we need to scan. So here's the new algorithm, again, translated into Ruby code. I'll go over each part. We'll start with the top section. So instead of having the starting VM frame for backtrace generation be the virtual machine's end control frame, we're going to use the VM's start control frame as the first frame. We'll still need the end control frame so we do not process off the end of the control frame stack. Remember that the reason that the old algorithm originally processed from the outermost frame and worked inward was to set the location information for cfunc backtrace locations when they were created. Now, this new algorithm cannot do that because at the time that the cfunc backtrace locations were created, we don't yet know the location of the calling ISEC backtrace location. So we need to keep a counter of how many cfunc backtrace locations have been added. If the length of the requested backtrace is not set, or it's greater than the number of frames, we just set the maximum backtrace length to be the number of frames. Now here's the main part of the algorithm, the loop over the control frames. Unlike the previous algorithm, this new algorithm loops from the innermost frame going to the previous frame in each iteration. It terminates when we have reached the end control frame or when the size of the backtrace has reached the requested length. So just like the previous algorithm, we only care about ISEC control frames with an instruction pointer and cfunc control frames. Now, assuming the control frame for the current iteration is one of those two frame types, if we are skipping initial backtrace frames, we decrement the number of initial backtrace frames to skip. Again, caller defaults to skipping one frame, but you can change this by passing a start argument to caller. Now for cfunc frames, if we're not skipping the frame, we add the backtrace entry to the array and we increment the cfunc counter. But this backtrace entry will currently not have location information. For ISEC frames with instruction pointers, if we are not skipping the frame, we first add the ISEC backtrace entry, and then if the cfunc counter is positive, we set the same location information to the directly preceding cfunc backtrace locations, and after that we reset the cfunc counter to 0. And then we can move on to the final section. And this section is only needed if the last entry in the backtrace is a cfunc frame, because in that case, we need to continue scanning the control frames to find the ISEC location to use for it. So we first check if the cfunc counter is positive. So if it's not positive, the last entry in the backtrace is already an ISEC frame, and the location will be set for it. So the scan uses pretty much the same criteria as the main loop, except we do not need to check against the backtrace size because we will not be adding to the backtrace. To find the location to use for the final cfunc backtrace location, we need to find the next ISEC frame with an instruction pointer. If we find such an ISEC frame, we update the location of the previous cfunc frames, and then we stop the scan. Now, switching from this old algorithm to the new algorithm took only a few hours. This new algorithm is much simpler than the previous algorithm. It's about twice as fast as the previous algorithm if you only need the previous optimized algorithm, if you only need the most recent backtrace location, and it's slightly faster if you need the entire backtrace. Additionally, during testing of this new algorithm, I came across an as-yet unreported bug in the previous optimization, which occurred when you requested a backtrace with the starting frame that was after an ISEC frame without an instruction pointer. Shortly thereafter, 2 additional bugs were filed in the previous optimization, one that resulted in a seg fault and one that resulted in an infinite loop. So while I thought the attempt to optimize the previous algorithm was at least a small victory, after the 2 previous bug fixes, turns out it was still a defeat. So I submitted a pull request for the new algorithm, which was merged and will be part of Ruby 3.1. I think it's in Ruby 3.1 preview 1. And then I think once again I can claim victory over this performance issue, at least until the next bug report comes in. All right. However, I still need to fix Ruby 3.0, and there were a few approaches I could use for that. One was reverting to the Ruby 2.7 behavior. However, reverting the optimization proved problematic because of unrelated changes to backtrace generation that were made after the optimization was committed. Another approach was backporting the entire new algorithm from Ruby 3.1 back to Ruby 3.0. And while the new algorithm is fairly simple, the actual change that was committed was large and invasive because it changed related data structures. So I chose a third approach, which was trying to fix the bugs in the previous optimization while still keeping the same basic algorithm. Now, it took me much longer to fix the previous optimization than it did to implement the new algorithm, but I was eventually able to do so. I ended up using a similar approach that the new algorithm uses. So this is the Ruby 3.0 code after the previous fix, which had this infinite loop, seg fault, and invalid result bugs. And here are the Ruby 3.0 changes to fix those 3 bugs. As you can see, we had to make changes in 2 separate places. So here's the first new block. Previously, we were just subtracting the requested frames to skip from the number of control frames. But that does not work if there is an ISEC frame without an instruction pointer before the requested start frame. So ISEC frames without instruction pointers should be ignored from the perspective of backtrace generation, since they should be basically invisible. We need to modify the code to account for that. So we start with the current control frame, similar to how the Ruby 3.1 algorithm starts with the current control frame. We run a loop over the control frames, going to the previous frame in each iteration. We stop the loop when there's no more start frames left to ignore, or when we reach the end control frame. And in each iteration, we decrement the number of start frames unless the current frame is an ISEC frame without an instruction pointer. So here's the second section we had to change. And again, this is also kind of long, so I'll break it into 2 subsections. So let's start with the first subsection. We need to keep track of the total number of frames we've seen, as well as the number of frames that will be included in the resulting backtrace. We also need to keep track of whether the last frame in the return backtrace is a cfunc frame. So like the Ruby 3.1 algorithm, we iterate over the control frames until we have found the requested number of frames, or until we reach the earliest control frame. Again, going to the previous control frame in each iteration. So the starting point for this loop will be the backtrace frame that we scanned to earlier when we were skipping the number of frames requested. If the current frame is an ISEC frame with an instruction pointer, or it's a cfunc frame, it will be included in the backtrace, and we increment found frames. We also record whether the current frame is a cfunc frame, because if it is the last entry in the backtrace, we'll need that information later. Regardless of the type of frame, we'll increment the number of total frames, and we'll use this to set the size of the control frame stack in later processing. Now here's the second subsection. First, we need to record the new starting point for backtrace generation. So this will be the frame we scanned to in the previous loop before the loop terminated. If the last entry in the return backtrace is a cfunc frame, we need to keep scanning to find the location to use for the last entry in the backtrace. So we'll keep scanning earlier frames. If during the scan we come across an ISEC frame with an instruction pointer. We found the location information to use for the final entry in the backtrace. So we record that last ISEC location, and then we can stop scanning. We then set the desired backtrace size to be the number of frames that we found. We set the total number of backtrace frames for the number of frames between the frame for the first entry in the return backtrace and the frame for the last entry in the return backtrace. We then set the initial frame for backtrace generation to be the frame that starts the last entry in the backtrace, and we set the backtrace generation not to skip any frames, since the backtrace generation process has already started at the frame for the last entry in the backtrace. So that's what the Ruby 3.0 backtrace generation code looks like after the fix. This is the code that will start shipping in Ruby 3.0.3. As you can see, it's even longer and more complex than all previous Ruby 3.0 fixes. However, it does fix all reported bugs in the optimization. Hopefully, there are no additional unreported bugs. So here are the lessons I've learned related to this optimization. First, do not be afraid of expanding your comfort zone by working on unfamiliar code. I had never looked at the vmbacktrace.c file before working on this issue. Often we as programmers have the idea that low-level code like databases and operating systems and programming languages must be impenetrable to newcomers. However, in general, it's just code. If you take the time to read it, you are likely to be able to understand it. Second, do not get discouraged when your first attempt at making improvements results in problems. In complex systems, it is impossible to test for all possible use cases, and you should expect that any significant change could cause regressions in untested cases. It is important to understand that regressions in untested cases are the cost of improvements. And finally, while you often don't need a new algorithm, sometimes you do. Try to recognize cases where what you were doing is difficult because of how you were doing it, and see if taking a completely different approach will make what you were doing easier. I hope you had fun learning about backtraces and how we optimize partial backtraces in Ruby 3. If you enjoyed this presentation and want to read more of my thoughts on Ruby programming, consider picking up a copy of Polished Ruby Programming. The book's publisher is currently running a giveaway to the book, to conference attendees, and the link at the bottom here is a link to the giveaway. And that concludes my presentation. I'd like to thank all of you for listening to me. If you have any questions, I got about 2 minutes. Does Aaron Patterson on Discord have any questions?
In fact, he does, but I want to give the audience a chance. Yes.
So hi, Jeremy. So this algorithm seems pretty complex, right? So I was wondering if there was like any unit testing or any kind of automated testing for these use cases?
Yes. So you're asking about the unit testing for the backtrace generation. Yes. So at all points when I committed something, it passed all tests. It did. I mean, it's not like I committed code I knew was broken. I mean, if all the tests passed, it just people kept finding additional test cases that didn't exist previously where it broke. So this is the importance of having a really good test suite that tests a lot of different cases. In a lot of cases, and I think Aaron can admit to this, the Ruby's core test suite could definitely stand to be improved. I mean, I think we'd be happy to take additional test cases that handle situations that are not currently tested. I think there might be a way to support coverage testing for C code in Ruby. I don't know how to do it. I've been a Ruby developer committer for a couple of years, and I don't know how to run coverage testing for Ruby core. Do you?
No.
Okay, there we go. I feel better now. I really do. Any more questions from the audience?
All right, I got one. Question from Discord from Aaron Patterson. What ISEC frames don't have instruction pointers?
Okay, so I probably should mention this. There exist internal functions. I believe they used to use a different frame type, like an ifunc frame type, but that was removed, and now they just use an ISEC frame type. These are internal functions like enumerable's group by method. Those are the things that cause all of these problems. Without these ISEC frames, without instruction pointers, this would have been so easy.
Is that the primitive stuff?
No, this is just way enumerators mostly I think use this. The way they work is they add these extra control frames which need to be ignored during backtrace generation.
Yeah, gotcha.
Is my understanding. Okay, 9 seconds. I don't think we have any time for more questions, but thank you very much. Thank you for coming here.
Thanks, everybody.